The climate is always changing. The good news has been that Earth's surface went from molten rock to currently supporting the bloom of visible life we see today as the Phanerozoic Eon. But the bad news is this bloom and the current wonderful conditions are just a brief moment, as the surface will naturally return to being too hot for any life to survive. Plus, as watching a volcano shows, things have cooled little inside the Earth, and while Earth currently has a relatively cool thin crust, relatively no thicker than an eggshell, it is almost entirely a very hot planet. This is not another video on man-made anthropogenic climate change. There are videos linked below on that topic. This focuses on the essential background for climate discussion, natural climate change, and reveals the key dangerous mistake in the climate debate. Natural climate change is far from being benign, has already been central to the extinction of over 99% of species of Mother Earth, and a greater understanding of this threat is key to dealing with both current and future challenges. Just maybe, while nature is awe-inspiring, it's not really simply a nurturing mother. Welcome to a One Finite Planet video that drills down from the environment over the billions of years of 4 eons and future Earth into the current and only time the Earth has been habitable for visible life, the Phanerozoic Eon, with the only term the Earth's climate has been suitable for humans being the very brief cooler times of the Phanerozoic that are marked in blue. Continuing through the Cenozoic Age of Mammals era and into our Ice Age, and then to the remarkable and almost certainly unprecedented stable climate of this Holocene epoch that has enabled Homo sapiens to suddenly progress from 300,000 years of Stone Age to our modern civilization. Then look at what's next for climate and how long before, if nature just takes its natural course, the environment would ensure we humans will just add to the over 99% of all species so far that have already progressed through the revolving door to extinction. We're in a race to have the technology to prevent climate making us extinct before it can cause the collapse of civilization that develops technology. Science and the Monty Python universe song have put in perspective how tiny our place is within the universe, but it can be harder to grasp how tiny our time is within not just the universe, but even within the history of the Earth. The Earth is 4.5 billion years old, and that time so far is divided into 4 eons. Hadean Eon? Think Hades of 1.2 billion years of hell on Earth with massive bombardments from space, intense heat, toxic atmosphere, no oxygen to breathe, nor ozone layer to block radiation. And yet, at some point in this eon, life began, perhaps even more than once. Life began with prokaryotes, highly resilient single-celled microbes, organisms too small to see with the naked eye, and like those we kill when cooking food and sterilizing medical instruments. Data from this time is scarce, as little survived the turmoil of the young, partially molten Earth, but that didn't even allow prokaryotes to thrive. Interestingly, though, life began, and perhaps can only begin, in conditions where visible life can't even survive. 2, the Archean Eon, named as the beginning for those 1.2 billion years when those simple microbes of first life began to thrive. This is the time of the late heavy bombardment, still no oxygen nor ozone layer, and temperatures still close to those of boiling water, but hey, those microbes are tough. 3, the Proterozoic, named as the time of earlier life for the emergence of eukaryotes. With no real oxygen and still too hot for complex life, this perhaps most remarkable evolutionary step, believed to have occurred only once ever, as microbes developed with a nucleus and organelles, which are like organisms within organisms, greatly increasing their complexity. These single-celled, still too small to see microbes, over time developed sexual reproduction, and then they exploded in numbers. Phanerozoic, meaning visible life, eon, 500 million years that began with the Cambrian explosion of life on Earth. Visible life, that is life we normally think of as life, finally emerged, with the very early Phanerozoic reaching peak life, more total biomass of life on Earth than ever before or ever since. The first three eons are sometimes grouped together as the Precambrian super eon, dividing time into 90% of the time the Earth was uninhabitable by visible life and the 10% habitable by visible life. Note that while the Phanerozoic, with oxygen, an ozone layer and more reasonable temperatures, all supports visible life, only 25%, as represented by areas shaded in blue, have had a climate that was potentially suitable for humans. Only 3% of the time has Earth been a planet that, had humans arrived in spaceships, they would have found suitable. A longer timeline is needed to include up to when, in around 5 billion years, the Sun will end its life as a mainstream star. A source for some useful data on the future for temperature and life is the paper Causes and Timing of Future Biosphere Extinctions by S. Frank et al. It's linked on the webpage as below, and diagrams from that paper are presented here. First, future temperature. It is often stated that life must end because the Sun explodes in 5 billion years, and yes, it may be true, but we've known for decades that, as can be discovered by a quick web search, all life on Earth will end far, far earlier, in just a fraction of that time, as Earth will continue to heat as radiation from the Sun increases every million years, and be too hot for any life of any type within around 1 to 1.5 billion years. While some articles, like this one, conclude that as the oceans won't boil for another billion years, humans must also have a billion years left. But while extremophiles and microbes may not have that long, that's far too optimistic for us humans. While maybe we can cope with more than the +2 degree increase, we certainly can't handle more than a small fraction of the around +80 degree increase needed to boil all the oceans. More on how long for us later, but this also raises another question. If the Sun is always getting hotter, does that mean Earth has also always been getting hotter and therefore must have been colder in the past? The Sun progressively sending ever more heat explains the hotter in the future part of that hotter, cooler, hot again trend, as shown in this diagram from Causes and Timing of Future Biosphere Extinctions, but not the hotter in the past when there was less heat from the Sun. The Earth was not colder in the past is known as the faint young sun paradox. Sun sent heat at only around 70% of current levels to the early Earth, and at that early time, a simple rock in space at our orbit, sort of like the Moon, would have had a temperature of -100 degrees C. But past heat can be explained by a combination of intense residual heat from the Earth's formation and CO2 levels, which were over 1,000 times higher than today, which made it hard for that heat and heat from the Sun to escape the Earth. As volcanoes show, not all heat comes from the Sun, and the Earth core is still hotter than the Sun's surface. The Earth has so far been cooling because CO2 levels have been falling by even more than needed to offset the increased heat from the Sun. However, we're about to experience the flip from an overall cooling planet to rising temperatures. Because firstly, while the CO2 level drop of around 4 parts per million can currently offset 1 million years of solar increase, we can only do that for around 25 million more years before CO2 becomes too low for plants. Secondly, while a rock in space would now be -18 instead of -100, or around 30 degrees cooler than our internal superhot planet, that gap's narrowing. And soon, even a rock in space would be too hot for life. The result is from hot to cooler and about to get hot again. The other point that may be clarified with some background in another chart is how come, if conditions in the past made the planet uninhabitable, life began so early on Earth. As in the song, sometimes words have two meanings, and the meaning in science can differ from the everyday meaning, as with the word life, which usually means living things we can see. We may say this antibiotic was life-saving, when in reality it was used to kill billions of microbes in order to save one single visible life. If all life is sacred, includes single-cell prokaryote and eukaryote microbes as life, then it would be hard to justify the existence of life like us that requires the deaths of billions of microbes every day for us to stay alive. Only prokaryote slash eukaryote microbes, as described by Professor Brian Cox's Just Slime, existed during Earth's whole first 4 billion years. The Phanerozoic, a unique blue of visible life on an otherwise barren planet. Earth as we picture it. Visible life, a breathable atmosphere, acceptable levels of radiation. Still, most often too hot for us humans, but if we, as aliens, found a world like this, we'd land and, Peter aside, not need spacesuits. For this most recent eon, we have more detailed data, as can be seen from the graph from Scott Wing of the Smithsonian. And that brings the first surprise of this Phanerozoic Eon of visible life, which is still too hot for us humans. Because there's not universal agreement on how to calculate global average temperature, leading climate figures usually, to me annoyingly, only give relative numbers like +2 or +1.5 without actual temperatures being clear. The Scott Wing chart and this video uses widely +0 to be 14 degrees C as global average. Note, a global average of 14 C is for all temperatures from the high maximum of weather reports to cooler night minimums. For example, New York City has an annual 13 to 14 C or 55 to 57 F, but days have reached 40 C or 104 F, and night can often drop below -10 C or 14 F. And no, an 8 degrees C rise in global temps wouldn't necessarily make New York like Sydney, Australia, even if it amazingly didn't break climate systems. That +8 degrees C globally could mean New York maximums of even 50 C or 122 F, much higher than the hottest of Sydney as it is today. Note the graph is half red and half blue, which brings us to another words have two meanings, Ice Age. The word Ice Age suggests a time with more glaciers / ice than normal, but while for day-to-day conversation, now must be normal, and the 4 degrees colder time just over 12,000 years ago, that's an Ice Age. But to a geoscientist, normal is that centre line of the graph, making now with those Greenland and Antarctic ice sheets, which would usually not be present, makes this at least an Ice Age light, or technically interglacial period of an Ice Age, with the just a little colder 12,000 years ago, a glacial period of an Ice Age. So, in science, as Dr. Ben Miles puts it,
that's where the terminology gets, I think, a little bit confusing. We are still technically in an ice age, just an ice age where the glaciers don't cover as much of the planet as they can do. We call this period an interglacial period.
There are attempts to find words to avoid the ambiguity that's been exacerbated by Hollywood, but we are now technically in the late Cenozoic Ice Age, and with temperatures currently a whole 9 degrees C below the 20 to 3 degree average for the eon as calculated by integrating the area under the curve, and even just below the 15 degrees C midpoint of temperatures in an ice age. Our time may not be the coldest the Earth ever gets, but it's really close. The geoscience definition of an ice age, a protracted period sufficiently cool for ice formation, in the Phanerozoic, sufficiently cool being taken as below 20 C, means 3 Phanerozoic ice ages, totaling 149 million years, or around 25% of the eon. While climate talks discuss the risk for humans of +1.5 C and +2 C temperatures during the Phanerozoic have ranged from -4 C to +20 C, quite recently +12 C, and on average +9 C. We humans have survived -4 C, but we've never lived through anything warmer than +2 C. As per this cartoon attributed to the Smithsonian, despite 70 metre to 30 feet, higher sea levels reducing the land area, maybe some of us could survive by moving to what's left of Greenland or the Antarctic. Conversely, it makes sense that while dinosaurs dominated the almost 200 million years between glaciation's ice ages, those dinosaur species of pre-asteroid time can't return or re-evolve and survive the current climate. The bird descendants can still be scary, but they don't include such giants, and they're all warm-blooded. Mentioning dinosaurs introduces the subject of extinctions. Climate change from Permian to Triassic, triggered initially, it is believed, by volcanoes, caused the biggest mass extinction of the Eon. The next biggest, the Ordovician-Silurian boundary temperature fall and then rise back again, with the rise now believed to cause the most extinctions, was again volcano-triggered. Then, third biggest, the famous meteor plus volcano-triggered end of the age of dinosaurs, led to cooling that, fortunately for us, is yet to end. Extinctions can also be opportunities. Peak life and a full planet came at the beginning of the Phanerozoic, and with total life on the planet now limited, mostly by the ability of photosynthesis to produce food, made life a zero-sum game. And the only way for species to significantly grow their population is if they, or something else, causes a decrease in the population of other species. The Phanerozoic's biggest extinction event produced the opportunity that became the Mesozoic Era, aka Age of Dinosaurs. The third biggest extinction event, the meteor, produced the opportunity that became the Cenozoic Era, aka Age of Mammals. But evolution is not only about doing a Bradbury or winning gold because of others fall over. Bradbury had to be good enough to reach the Olympic final. Species that reach abundance have to have already been good enough to be waiting in the wings for their moment by virtue of previous successes on a smaller scale. Prokaryotes began in small pockets in conditions on the Hadean that became far more common when in the Archean, allowing them to thrive. Complex life began in the Precambrian in limited numbers and then thrived in the Phanerozoic once the changed atmosphere meant sufficient oxygen was available globally. Small nocturnal mammals existed in the Mesozoic age of dinosaurs. Then, when temperatures fell, they could thrive even in the heat of the day and survive with larger and larger body sizes without overheating. Mass extinctions are now known to be just spikes within a constant stream of extinctions, largely due to continual climate change, which can happen on timeframes too short to show on graphs with such long time periods. While the chart of the entire Phanerozoic Eon reveals more detail on temperature than on the full timeline chart, consider the Cenozoic Era of Age of Mammals chart. At the very right, temperatures are shown to continually swing by 6 degrees C so many times per million years that the whole area around the red average line becomes shaded blue. Yes, the expanded timelines on shorter timeline period graphs allow for more detail, but also the more recent the time, the more data we have, which is why on this era level graph, the blue detail line shows more data as the plot moves from 60 million years ago to the present at the very right. The entire Cenozoic Era is known as the Age of Mammals, but the largest mammals of the earlier, hotter Cenozoic were all small, limited to 5 kilograms in size. An example from 50 million years ago being the common ancestor of the egg-laying platypus and echidna. As temperatures progressively fell, the size limit for largest mammals increased to 50 kilograms, but it was after the Cenozoic Ice Age began that the first human-sized mammals appeared. This began the time species like humans could evolve and exist, and by the end of the Paleocene, the largest mammals had reached 750 kilograms. All our mammal and ape ancestors, going back 30 million years, evolved in these below 20 C Ice Age conditions, including the first apes, not our ancestor actually at this time, but the oldest mammal not yet extinct, the last common ancestor of humans and chimps, the earliest human species, the first evidence of stone tools and start of the Stone Age, the start of the Quaternary period, and then the age of Homo sapiens, and then the end of the Stone Age. The Cenozoic Ice Age is the habitat of humans. We're from an ice age in the coldest period of the coldest era of the coldest eon of Earth's history. Although we aren't currently in that coldest phase of an ice age, most of human and Homo sapien history has been in that coldest phase of an ice age. Blue, coldest ice age glacials, and not quite as cold interglacials, shown here. Yes, it's popular to take ice age to refer only to those up to 4 degrees C, even colder extreme of glacial period. And while Ice Age films illustrate how different just 4 degrees C can be, consider how different it also was during the near 6 degrees C warmer than now in other times during this Ice Age. Within the overall 10 degrees C of an Ice Age, there's a wide range of conditions, but it's useful to have a label for the very different cool 10 to 20 degrees C conditions of an entire Ice Age, in contrast with the more prevalent much hotter 20 to 35 degrees C conditions during the rest of the Phanerozoic. The geoscience label Ice Age temperatures range from 10 to 20 C, which puts the 14 to 14.5 C current below the middle of the Ice Age temperatures. Perhaps there's too much changing of what words mean to make people feel better, and we should stick to the reality that on Earth, big sheets of ice does mean an ice age, and we do live in well below typical temperatures. When you look at a graph of climate over 2,000 years, it's not always changing, but remarkable stability, at least until 1950. Yes, the medieval warm period may have been warmer in Europe, but it wasn't warmer noticeably globally. And while the Little Ice Age was colder globally, and only by half a degree C. But zoom out a little, past significant changes come into the picture. The period of stability coincides with the time of civilization.
We've had a 10,000 year period where our civilizations have developed, where we've had an enormous privilege of a planet at 14 degrees Celsius plus minus 0.5 degrees Celsius.
A period of stability like this has never happened in the past human history, and probably never in the entire Earth's history. The odds against such a period of stability at a special time of accessorized evolution, as discussed in the video linked below, must be truly astronomical. Think about it. The Stone Age lasted 3 million years. More specifically, Homo sapiens remained in the Paleolithic Old Stone Age for 300,000 years. Then it changed to a stable climate, and in just 12,000 years, we move through the New Stone Age to space and the internet. An unprecedented climate combination of stability and the ideal temperature, just at the time a species able to evolve its tools accessories is ready to seize that window. On every planet where these two events coincide, it may result in a civilization like ours, with intelligent beings watching internet videos. But within the at least 100 billion planets in the galaxy, looking at the odds, there may not be many places where this is happening. Unless either nature or humans manage to sustain this climate stability, the current conditions that support 8 billion people will end. How long the stability will last naturally is unknown, and while there are stats on how long previous interglacials have lasted, no previous interglacial looks at all like this, and so it could end any time. At every level, once started, temperature changes just keep going in the same direction until something turns things around. At the biggest picture level, we know the story. Earth is normally too hot for anything but highly resilient microbes, and at the million years time frame, things will just start getting hotter and hotter until we leave, intervene, or die. At Phanerozoic level, sure, the Earth has typically been at least plus 9 C hotter in the past, but while we humans have no history of surviving beyond plus 2 C, as long as things remain in the Cenozoic Ice Age, we're okay. That makes the immediate question, what's next for our Cenozoic Ice Age? Particularly that temperature spike. The video linked below from Dr. Ben Miles suggests that the Ice Age could end.
If we are in a termination-like event, given that we're in an interglacial period at the moment where the glaciers are already receded, could this knock us out of an ice age entirely?
Logically, there are 3 possibilities. The current spike could just go away, but it doesn't match what has happened with any previous spike.
Which further propagates warming of the planet. As the ice begins to melt, darker ocean or land surfaces are exposed. These darker surfaces are better absorbers of sunlight, which leads to further warming and more melting. As the process continues, the Earth enters a rapid warming period called full deglaciation, with significant further ice melt and a corresponding rise in sea levels over a very short period, usually over a matter of just decades.
Temperatures could now start falling as they have done previous times climate approached +2. Those previous times did look very different, but temperatures started to head slowly down to a deep glacial ice age. Surviving a deep glacial ice age wouldn't be unprecedented for humans, and perhaps we know how to stop the planet cooling. Temperatures remaining at spike level or rising further would start a chain reaction for further warming as ice melts. The spike rising beyond +2C does take temperatures to unprecedented levels for humans. +3C would take it to unprecedented levels for any mammal over around 5 kilograms. And the speed of the temperature rise means it threatens far more species. In summary, all three possibilities are technically possible, but it's most likely the third one of the spike staying or rising further, which means we need to take some action regardless of whether it's natural or man-made. How long have we got? Well, it may be unwise to ignore the signs. Consider why we're vulnerable. As a civilization going from under 2 billion to over 8 billion people in 100 years is like extending the population onto floodplains without caring about 100-year floods, or setting up camp in the desert just after rain and expecting to be able to stay. We can survive the Phanerozoic's coldest so far, and perhaps up to 6 degrees warming, by just restricting the latitudes where people live and sheltering, but we can only do it with a whole lot less people. As explained in the links in the web version of this video, surviving anything approaching over 8 degrees C, which is near the Phanerozoic average, would require some remarkable new technology. Species actually never last. Remember the extinctions graph? All species have a time limit, as per this quote from a research paper on living fossils. So, without using our capacity as the first species with accessorized evolution, linked below, to rewrite the rules, we have at best only a few million years, even without considering the current temperature spike or other environmental boundaries. Dinosaurs survived 180 million years, but dinosaurs includes between 10,000 and 25,000 different species. No individual species survived anywhere near that long. There was a mass extinction event during that time when temperatures plummeted to not as cold as the around 14 degrees C of today, but did dip briefly below 20 C. Different times had different species. For example, Stegosaurus existed for 10 million years. Triceratops survived 3 million years, and various Tyrannosaurus family members, including T-Rex, altogether overall survived almost 6 million years. Even with animals like crocodiles, often quoted as having been around since the age of the dinosaurs, it's the crocodile family that's been around for over 100 million years. And while the current species look to us a lot like their ancestors, individual crocodile species alive today have existed for typically 10 million years or less. Still long-time survivors, but they have a reptile metabolism, live only in a narrow range of the warmest habitats of our time, and spend a lot of time in the water. We are a homeotherm, temperature-inflexible, large, warm-blooded mammal that evolved during an ice age, without special heat coping mechanisms of other mammals such as heterotherm elephants or camels, and we don't have the metabolism or design to survive high-temperature days that would happen in conditions like those of the age of the dinosaurs. Just as the only dinosaur descendants able to survive now evolved to be adapted to colder climes in ways that, fortunately for us, limits their size. How long we've got depends on whether we means us as a society of nearly 8 billion, or a holdout group underground near the poles using special technology or something. The risk of change that reduces the population and forces relocation to different areas is far greater than that of total extinction, and would come first anyway if we were headed for total extinction. If society collapses to be no longer capable of the science and technology to develop control of climate, then our end becomes inevitable, as chances of a repeat climate stability to build a new civilization is unrealistic. These things considered, it all comes down to a race between nature and our developing the ability to manage and control climate. If only considering the data up to 1950, I would have thought that most likely we'd have another 500 years to perfect solutions. And as discussed in the next population explosion, linked below, all going well, we'll need to expand beyond Earth in around 500 years anyway. But given the data since 1950, in particular since 2020, if the spike passes plus 2C, which currently seems inevitable, then, as Dr. Ben Miles suggests, we could fully exit the Cenozoic Ice Age within decades, which would lead to devastation within the lifetime of those being born today. I'm going to allow confirmation bias and optimistically answer, even if we pass plus 2C in the next 2 decades, if we could perhaps find a temporary solution before too much ice has melted and buy some time, then we could still have 500 years deadline before having a full solution. But that's a big if. The narrative, we live on this wonderful planet that's naturally nurturing for humans, is just, to put it mildly, totally wrong and dangerous. Though sure, nature itself would never cause species to become extinct. The over 99% of all species that so far have already become extinct learnt that existence is fleeting and nature is ruthless, as they all experienced a time when their entire next generation all died. Those species had their moment while climate suited them, just as this current, so atypically cold for Earth that it has polar and Greenland, etc., ice-covered areas, now provides us our moment while climate suits us. But the pattern of nature is for every species, that moment ends, and nature will soon ruthlessly abandon us for species evolved to survive a hotter climate more typical for Earth. Curiously, righteous environmentalists and climate risk deniers have in common faith that nature would continue indefinitely to provide a climate suitable for us humans. One extreme would believe nature is nurturing, but humans defile it and can destroy it. The other with belief nature will remain nurturing no matter what humans do. We need to reject the false narrative of a planet always nurturing for humans and replace it with, we're living in an amazing but fleeting time when Earth provides an environment that suits us so perfectly. And accept that we only exist in the window of a highly improbable opportunity that will close if we don't gain the ability to ourselves keep it open. That we have evolved to have this possibility is amazing, the result of a combination of events perhaps unique within the galaxy. The natural outcome would be for it to all vanish into nothing as the Earth inevitably continues on the path to becoming just another lifeless planet in space. To what extent it is humans or nature causing the current temperature spike makes little difference to the reality that we must find a way to stop it, not to save the planet, but to avert or at least delay a mass extinction event that will become the natural progression ending the age of mammals and including us humans as an early casualty. A look at current trends and to what degree it is us closing the window of our time prematurely versus nature closing it for us will be explored in another video, which will be linked below.